So guys, the rectangular tank has been loaded in mechanical APDL. So let's check what all the materials that have been assigned. Okay, so after selecting the geometry, you can just select this geometry here and the rectangular tank, and this is the bottom portion. Only the rectangular tank, you can see that it is a BBM, that is burnt brick masonry. So this is fine with us. And if we see the rectangular tank here, so just deselecting this part, we'll just say that hide body. Okay, so only we have this rectangular part here, that is a base is made up of a concrete. Okay, there is a 200 mm thick concrete. So this is a concrete property. Okay, just show all bodies. Yes, now let us come back to the analysis part here. So let's begin the analysis. So connections, we'll just check the contacts here. So this is a contact region, so this part is in contact with this part here, and this everything is fine here. Okay, so fine. Then what we are going to do, we are going to take a mesh here. We are just going to select a default mesh. We'll say generate mesh. Okay, so this will take small time here. Yeah, definitely done. So the meshing has been completed here, my dear friends. So now what I'm going to do is I'm just adding the boundary conditions. So let's add a fixed boundary conditions at the base. So let it be a plane here. So our base is fixed. Okay, the part of base is fixed. And now we are going to add a pressure. We are going to add a water pressure. So let's see what we can do here. Insert. Now we will add pressure. Okay, so to simulate pressure due to fluid weight, so we will add a hydrostatic pressure here. So what we are going to do is we are going to add the hydrostatic pressure at the portion here. So we are selecting the face here. So this is the place at the bottom of the slab where we add the hydrostatic pressure. Hydrostatic, which means hydro means water, static means the water is static. It is not a flowing water, so it's a static hydrostatic pressure. So just add, apply section geometry. Yes, fine. Now just see the highlighted yellow strips here. So we have to give the fluid density. Okay, so we have to give the fluid density. So the fluid density is we know the density of water. Density of water is 1000 kg per meter cube. 1000 kg per meter cube. So if we calculate it in if we want that in kg per millimeter cube, we have to convert that, and this is the pressure. So let's select this as components here. So we'll see that it is in the negative y direction. Okay, so negative y direction, we want the pressure to be in negative y direction. So let us assume that there's a 100. Okay, let's suppose assume that there's a minus 50 mm per meter square. Okay, minus 50 mm per meter square is the pressure. Okay, we'll just see that what happens. Now I have to select the fluid density. So let me check that. So guys, here the fluid density is asked in kg per millimeter cube. Okay, so this will be that 1 millimeter cube. The 1 millimeter cube means 1 mm in 1 mm length, 1 mm width, and 1 mm height of the part of slab will hold how many kgs of water. So this is a very small value that you will get, because the fluid density, that is the water density, is 1000 kg per meter cube, but it is meter cube, but here they're asking for a millimeter. So after calculation you will get that as 1 into, so 1 e raised to minus 6. Okay, you can verify this. 1 e raised to minus 6, this is the fluid density. And you can see that I am putting a hydrostatic acceleration. Okay, so ordinate, free location, surface, x coordinate. Okay, fine, everything is fine here, done. So let's start the analysis here. Now this is 200. Okay, everything is fine. So let's begin. The solution will just say here everything is fun. Now we'll say it as solve. Okay, so we have given a solve option here. So this started solving now. Okay, it will take some time. I'll just load when the results are ready. Okay, so guys, all the green ticks indicates that the model has been solved or analyzed completely by FEA techniques, finite element analysis. Now we'll just insert deformation, total deformation we are going to insert, and one more thing that we will insert as immediately is maximum principal stress. Okay, we'll just say again evaluate all results. Okay, so the evaluation has been done. So my dear friends, you can see the total deformation here is absolutely 0, and the maximum principal stress we are going to see here, the maximum principal stress is 0. So let's check this. So guys, we haven't got any deformation here since this base is fixed here. So what I have done here, I have created a fixed base, so we haven't got any deformation, and maximum principal stress and minimum principal stresses are also 0. But what since we are using a bonded connection here, just see that the rectangular lateral surface area, or we can say the lateral surface area, is connected to the base. Means the contact body is lateral surface area walls, and the target body is our concrete base. So here we consider this entire structure to be a bonded structure, hence we don't find any forces generated there. So for this hydrostatic pressure, now what I'm going to do, now I'm just adding one more thing here. We can insert one more thing, that is only pressure. We can only insert pressure here. Okay, and we'll just check with that. Okay, we'll just check with that pressure. Fine. So this is a surface effect, normal 2. So we'll add pressure here. Fine. Apply section. Yes, now we have added pressure. Now let us say we have it in megapascal. Okay, we will have it in megapascal. So we'll say megapascal is nothing but Newton per millimeter square. Means we'll have first 50 Newton. Let's say it is having 100 Newton per millimeter square. So let's check this. Okay, 100 Newton per millimeter, 100 ampere ramped. Okay, we'll just suppress this hydrostatic pressure. Suppress. Okay, now we'll just say solve. Okay, it's loading. Okay, fine. So my dear friends, you are able to see the total deformation here. I have not changed any boundary conditions as of now here, but you are able to see that there's a, let's say, probe maximum minimum. Okay, so we are just saying, so maximum pressures will be at the edges here. Okay, at the edges here, and the minimum pressure will also occur somewhere. We have to see it here. Minimum occurs on rectangular tank. Okay, fine, this is fine here. So we'll run the animation here. So I'm just understand the behavior of this material. So we can just see the total deformation here. It is fine. So now we'll see maximum principal stresses, where they are getting generated. So we're able to see there's a small buckling here, like there's a small buckling of the walls, like what you can say, with the pressure of water. So just see this part here. Okay, I hope this is fine. So maximum principal stress is 12.428 Newton per millimeter square. Okay, let's see one more thing that we can just see here is linearized stress. So maximum equivalent stress, maximum Coulomb, and maximum. Okay, so we can just see one more result here. Probe. We can have a stress here. So what we can do is stress tool maximum tensile stress, maximum equivalent stress. We'll have the safety factor check. Okay, we'll see the safety factor check here. So this is a safety factor check here. Okay, fine. So this is stress tool. That one more thing what we can see here is energy. So middle principle, normal stress. We'll just see the normal stress also. Normal elastic stress. Yes, we'll come to know the maximum is occurring at the edges here. So you can just see the edges here. These are the red color here. The red color means your base will be under maximum compression. Okay, so the base will be maximum compression. You can just see this part here. So this is the way it has been loaded here. Okay, now what we are going to do is we are just going to increase the pressure as of now. So we'll just increase the pressure here. Okay, we'll just go increase the pressure here, normal to. Okay, so we'll have this component vector normal. So we'll have a component here. We'll just make this minus 200 megapascal. Okay, we'll have make this minus 200 megapascal. So we'll say it as a solve. Okay, fine. So we'll see. Okay, fine. The results are ready here. We'll see the maximum principal stress. That is what we are very much interested to know. So we are seeing the 24.856 Newton per millimeter square, which means that our material has not yet failed here. Still the material has not yet failed, because so you can just see this part here, how it is getting compressed. See the parts, the stresses are getting generated, accumulated here, and the normal elastic strain. So just see this part here. This is a normal elastic strain. So I hope you have understood how to calculate this. So safety factor again. So minimum also is here. Okay, fine. So I hope this is clear. So that's it for today's video. Please do subscribe my channel. If you like my video, please share this video to your friends, and we'll meet in my next videos. Thank you. Take care.